we have several product families. We have what we call MegaSwitch 2, which encompass our 2012, that's the 10100 switch with a single gigabit uplinks. And the next level, or the next generation after that, is what we call the GFS. That's the gigaframe switch. Now, the GFS is basically almost a completely new design of the MegaSwitch 2 architecture. So what I'm going to talk about now has some roots in the MegaSwitch 2, and you will find out a little bit more about it later when you get a presentation about the MegaSwitch 2. So perhaps I should just start with some basic facts about the GFS, and then we can maybe go into more details and see how it's implemented internally. As far as capabilities, the GFS is presently housed in like a chassis configuration where you can have 3 slots. It has basically 4 slots actually, where 1 slot is dedicated for control and 3 other slots are dedicated for ports. The maximum configuration is either 64 ports, up to 64 ports of any type. However, presently it is configured such that it can be configured with 12 ports of gigabit, or a mix of gigabit and 10100, up to 64 ports of 10100. In terms of what's available today for the product, there's the 4-port gigabit module, which has been shipping for a while, and that's in any configuration of optical single mode, multi-mode. And we're in the process of introducing a 16-port 10100 module. In the works, what we have in process is we have what we call our frame processor module. That's a module that would enable both traditional IP routing and will enable 802.1q tagging and detagging. Now, what we have today in the GFS in terms of performance is basically, if we highlight the various items, it's up to 64 ports. It's an 8 gigabit backplane, and we'll talk a little bit about that more. It can filter or forward frames at up to 5.4 million packets per second. Oh, I should write frames, packets per second, never mind. Packets per second. And its address resolution engine is capable of making decisions on any of the following pieces of information. There is the source. Let me just get this eraser here. There's the source MAC. There's the destination MAC. There's the source port. There is the protocol ID. And there is the VLAN tag. Okay. Now, the forwarding decisions are made based on any of these parameters, and regardless of what type of conditions you set up or relationships, we sustain the forwarding rate because it's a single flow pipeline. And we'll talk a little bit about it more. Now, these are the basic statistics on it. Now, in terms of internally how it's designed, we have a couple of slides that Mannix is in the process of copying some more and hopefully making some transparencies. But I will start with maybe as a very basic diagram of it. And we have basically, if I were to draw this, we have this, assume is okay. This will be the this will be, for instance, a Mac. Then we have a these are the data buses, and we'll discuss in a minute some more. We call this is the address resolution logic, and this is what we call our Q slash arbiter management. Okay, so essentially, if we were to follow how frames propagate in the GFS, on a very simplistic level, frames come into ports. The header of the frame gets forwarded to the address resolution logic, and that's essentially where the decision is made as to what to do with the frame. So one of these bullets here shows what type of parameters the address resolution logic looks at. So in here you can make a decision based on any of these, or combination or all of them, as to what to do with the frame. Once that's done, the information is passed on to the queue manager. Now the queue manager is basically like the traffic cop in the switch. It basically makes a decision as to what goes from where to where when it goes. And if you look at it, it actually knows about every single frame in the switch. So again, what happened is, packet comes in, the header gets stripped, and it gets passed to the address resolution logic. This happens to be a bus that's 36-bit at 33 megahertz right now. And in order to sustain the packet rate that we talk about, you can easily calculate that every header is equal to six 32-bit words. Okay, and that gets passed on this bus. Now this is a single direction bus. So once that information is queued in the arbiter has a mechanism to signal the ports what to send when. So it both manages the data buses, and it also decides about the order. Now that's sort of important because that determines the behavior of the switch. I mean, you can make a switch that is able to set priorities and flow control, quality of service, etc. That's all controlled through the arbiter. Now, so again, continuing the simple packet flow, a packet would enter a particular port. The header will get stripped out into the address resolution. The result will be passed to the queue manager. When that packet is completely received, or when the port indicates that it's ready to transmit, then the arbiter would signal that input port to go ahead and start transmitting this packet. So what he will tell him is, put another port here. So what he would say, for example, is go ahead and send a packet from this port to this port on a particular bus. Now, the reason that's important to notice is because traditionally you can make switches, and there's several ways of architecting switches. You can design a switch such that all the packets are stored in a shared memory. And the advantage of that, of course, is lower cost usually. You could also design a switch where all the packets are completely distributed in the ports. So every single frame that enters gets stored in a port and then gets copied to all the other ports that it needs to. And you can also design a hybrid of these things. Now, in a shared memory, you generally have a single path to the memory. So there's a single bus in the switch. Now, in completely distributed architectures, you have several ways of connecting them. You can connect them with a single bus, which is generally the simplest and most cost-effective way. But then, of course, you lose on the data rate. Then, of course, you can also connect it with what's called a full matrix. A full matrix is sort of a mesh between all the ports. So you could have basically any input. You can imagine any input can talk to any output. So you can have simultaneous transactions. You can have, in fact, the number of transfers ideally could be equal to the number of input queues / output queues. Now, what we chose is something that's in between. We don't have a full matrix, but we have actually two buses. So that allows us to start two transfers at once. So we can actually transfer two packets simultaneously on the bus. Now, packets on this bus go start of frame to end of frame. So a complete packet gets transferred. It's not a TDM bus, meaning it doesn't transfer cells or portions of packets and then they get reassembled. Now, the advantage of doing it this way is because you're utilizing the bus to its fullest capacity. In other words, on this bus, only packets get transferred, complete packets get transferred, and only data of packets. It's a beginning of a frame to an end of the frame and nothing else. There's no overhead information, such as where the packet should go and what to do with it, because all that overhead information is processed via a separate path. So for example, again, let's say this port received a packet. The header gets stripped and goes to the address resolution logic. The information about this frame gets passed on to a queue manager. The queue manager will then signal the input port, which I will now start calling a queue, the input queue, to transfer that particular frame to a particular output queue. And that signaling happens on a separate control path, which I just indicated here. You can imagine that this control information is actually distributed among all these basically queues down here. So that frame, in its entirety, starts getting transferred on one of the buses, ends up at the appropriate queues. Now, once it's in the appropriate queues, then it gets queued out for transmission and gets sent out. Now, that's the simplest and most basic transfer mechanism. And actually, what I'll do when we're done here is maybe I will explain a little bit in more detail how we support many ports and maybe a little more detail about the memory management. So that's how a packet travels. Now, we also have, of course, management, SNMP, statistics, etc. And architecturally speaking, it's sitting on one of these buses. Actually, let me draw it this way. Imagine you have now that's simply to collect statistics, to talk SNMP, to boot the switch, to run a self-test, etc. And that CPU actually sits on one of these data buses, and in addition, there's a separate so-called CPU control bus that all the queues and all the devices are connected to. That's a completely separate bus. And this is actually a 16-bit bus. Okay, that's only for gathering statistics, setups, initialization, etc. So we'll write down here again, CPU bus. Now this is This is data bus, what we call A, and let's call this one data bus B. Okay. Now, as far as the way the switch gets partitioned, we said before that we have a control module and we have port modules. Everything you see in the upper portion here, I would say, if I were to cut it actually, everything you see up here that's the control module. Okay? That includes the address resolution logic, the queue management, and the CPU engine. What you see down here, well, I mean over here, okay, over here that's the backplane. Oops, excuse me. That's the back. Okay, so these are just essentially, if you will, wires. That's the switch backplane. And what you see down here are the port cards. Okay. Now, in terms of performance and speeds, NBase has actually a unique way of designing these data buses. These data buses are what we call asynchronous buses. What that means is that once a particular queue gets control of the bus, then that queue determines the speed at which the data gets transferred on that bus. It's not a constant clock that goes on this bus. Now, the buses are designed to run they are basically, each bus is a 72-bit bus, because there's some control information that gets passed. And they run at up to 66 megahertz, each one of these buses. So, so you have two of these. And that's why we claim a peak performance of 8 gigabit. What that peak performance means is literally you should be able to have 8 gigabit streams going in and 8 gigabit streams going out. However, that is determined by the type of port cards that you're using. Because, just like I said before, the device that owns the bus is the device that determines the speed at which the data gets transferred. And of course, the data will have to be transferred at the lowest common denominator of the queues that are destined to receive this frame. So, now the benefits of doing it this way, of course, is that allows us to be somewhat more flexible and upgradable. In other words, our next generation gigabit module, which I haven't talked about, will be running at the full speed. And in addition to that, we'll also do what we call local VLAN tagging and detagging. And that will do is that will enable us to improve the performance and the bandwidth of the switch without upgrading everything. Now, also today, every single module that we released so far is designed to be able to receive it up to maximum rate. So right now, every time you get a new module, depending on what's the maximum rate it can transmit, it will be able to utilize this. Okay, so this is just kind of a basic concept. Now, if we go into more detail, how do we hang more ports? Well, down here, logically speaking, we allow up to 12 what we call queues. So imagine now, rather than writing down here an actual network interface to each one of these, imagine now that what you have sitting here, rather than say a gigabit MAC, you have what we call a queue. Okay, and let's say this is Q1, 2, and this is Q12. Now, behind each one of these queues, you can have n ports, n physical ports. Now, the total number of these, this may be n1 ports, n2 ports, n12 ports. So that's some number of ports. However, the total number, if you sum all the numbers, the total number must be less than 64. Okay? So the arbitration system actually deals with what we call 12 queues. And in the case of gigabit, actually, now you see where the 12 gigabit comes from. In the case of gigabit, we actually assign a queue per port. However, in the case of 10100 ports that require less bandwidth, we can assign multiple ports per queue. So for instance, in the 16-port module, we're actually assigning 4 ports, 4 10100 ports to every queue. In our next generation module, which is a 24-port 10100 module, we're actually going to assign 8 ports per queue. Now, the way this information gets passed along is the address resolution logic actually does forwarding decisions based on the port level. So you can create VLANs, port VLANs, various rules between ports, port mirroring, etc. The queue management, the data transfer system, works on a queue level. Now, once a packet enters a particular queue, once a packet has been transferred from one queue to another, along with that packet, we pass additional information that instructs the queue what to do with that frame inside the packet. So on the most basic level, that would be to which port to go. On a more complex level, it might tell the port also, okay, what VLAN tag to send it with, and whether the packet needs to be routed or not, and if so, how to route that packet. So that's a second level of complexity. And again, the important thing to note is that this is, I mean, you can have actually 2 transfers happening simultaneously. We can have, for instance, one packet going from, say, this queue to this queue on this bus, and you can have at the same time this queue, for instance, sending a frame to another one on a different bus. Each one of them is connected to both, but it can connect and be active on one at any one time. So we can transfer 2 at the same time, simultaneously. Now, the other nice thing about doing it this way is that if you have any multicast frames, any broadcast frames, they don't get transferred twice on the bus. The bus is extremely efficient. Every frame that enters the switch, if it doesn't get filtered at the input, then it only appears on the bus once. If you have, for example, what we call shared memory architectures, which are more cost-effective, however, the drawback of them is, imagine you have all these ports here, and this is a shared memory. This is shared memory. Imagine you have this architecture of shared memory, then every packet needs to go to the memory once, and then needs to be read out of the memory. So it physically appears twice on the bus. So to accomplish the same thing with a single shared memory, we would need a 16 gigabit worth of shared memory in order to say that we have 8 gigabit of bandwidth. So that's actually very important. And what it actually means to a customer is it literally says that you could have potentially 8 gigabit streams coming in and 8 gigabit streams coming out at the same time. Now, it's debatable how you present it. Some people might present it as 16 gigabit because you have 8 going in and 8 going out. But in our design, that's presented as 8 gigabits. So you could literally do 8 gigabits in and 8 gigabits out. However, again, I want to stress the fact that this depends on the modules you're using. The modules that we have, the gigabit modules that we have right now, are operating at 33 megahertz transmit rate. Okay? And the 10100 modules that we have are operating at 33 megahertz transmit rates. The next generation gigabit module will be operating at 66 megahertz transmit rate. So you'll be able to get the full capacity of the switch then. But then again, of course, everything depends on what you need. I mean, a 16-port 10100 module doesn't require such enormous bandwidth. You have only 16 ports, that's potentially 1.6 gig. So you really don't need that speed.
And the information, all rows gigabit.
Okay. The packet memory is distributed in this case, right? All the data is stored in every queue. Every queue that doesn't necessarily serve a single port. However, in the gigabit case, if we restrict our discussion to gigabit case, then every queue stores the data for one port. However, the address resolution logic is shared among all the ports. So all the header information is stored centrally. All the header information goes through the address resolution logic, and all the subsequent result of the header analysis is stored centrally in the queue manager. However, once it's at this rate, this is essentially a single word per frame. So the amount of data that's moving here is substantially lower than is required to move actual data. I mean, frames can be anywhere between 64 bytes to over 1,500 bytes. But the header, as I said before, is a constant 6-word header, which is basically a 24 bytes, 6 words of 32 bits, which is 24 bytes of data. And the subsequent result that gets passed to the queue manager is a 32-bit result, actually a 36-bit result that gets stored per frame centrally. Okay, actually, you see, the shared memory I drew here is just to demonstrate a different architecture. This is not what we're using. Okay, this is not what we're using. We're using distributed packet memory. So you literally have, in the case of the gigabit, again, a separate memory for the packets per port, okay? But the header processing is all done centrally. And in fact, we finally got our slides, and what we can do is we can go again through a packet walk, which basically will tell you how a packet is forwarded inside the switch. When the frame first enters the switch, then part of the function of the input queuing is to take that header out and send it out on a separate bus. See, on this separate bus right here.
So
Maybe I should highlight it with a different color.
That's at each port?
At each port.
Not on a module.
Here, just a moment. Okay, basically, at each blade, on each card that we have, depending on the card, in the case of the gigabit, on each separate port, okay, there's a little controller, and that controller, when the packet comes in, and it stores the data in the private memory of that port, it also strips the header and sends it out to the address resolution logic on this address bus. So that function, the stripping of the header, okay, is done locally at the port card level. Now, whether it's done locally per port, that depends on the actual module that you have. In the case of gigabit, because it's a higher bandwidth interface, it's actually done per port. In the case of a 10100 module, for example, it's done globally for all the 10100 ports in one place on that module. This is an overview of the most basic aspects of the switch. So just to review, just to make 100% sure we're clear, we have a layer that we call a ports, logical layer that's ports, and that logical layer, the number of ports cannot exceed 64. And those ports are sitting behind what we call queues. Queues are essentially, if you will, places where you store packets, memories where you store packets. Our system today can handle 12 separated queues. So it's like, imagine you can have 12 banks of memories. You can call them local shared memory or private memories. It depends on what type of board, what type of network interface you have. In the case of gigabit, it's a private piece of memory per port. In the case of 10100, it can be a shared memory for several ports. Okay? Then after that, we have the arbiter, which basically manages packets that are inside queues. Those packets, once they entered, are controlled. The transfer is controlled through the arbiter. Once they are at the output of a particular queue, then they get sent out under the control of the local port or the local blade. Okay? So if we look now, if we make a little drawing of the two modules that we're shipping today. In the case of the gigabit module, actually, I'm not going to change anything in this drawing because a gigabit module is essentially a separate, it's just like the original drawing that I drew before. The gigabit module is basically, this is basically a separate piece of memory. This is one piece of memory. There is the MAC, and there is your port. So in the case of a gigabit module, you have 4 of these duplicated on one blade. And that's it. And all the functions that you just asked about, how does the header get stripped? Well, every port has its own little controller that strips the header to send it up. Every port has its own memory. Every port has its own connection to the 2 buses. Okay? Now, if now I erased this part, well, actually what we could do, perhaps we can extend this little switch here. And if I erased this, and we can kind of get a logical view of what a 16-10100 port blade is. Well, a 16-10100 port blade actually looks like okay, so physically speaking, a 16-port 10100 module is implemented with a single shared memory for all 16 10100 ports. And this shared memory has basically 2 sides to it. It has what we call the bus side, which is the side that can transfer and receive from the bus, and the port side that can basically send and receive frames from the 10100 ports. Logically speaking, this shared memory stores inside of it 4 queues. So to the queue manager, this logical shared memory looks like 4 queues. He can ask Q1 to send, he can ask Q2 to send, Q3 separately. He can manage all 4 queues separately. However, physically, the way we implement it on the module, rather than have, like in the gigabit case here, where we have, like in the gigabit case, where we have a single queue and a single memory, a MAC, and a single memory and single MAC separate, what we have here is a shared memory for 16 ports. So that's how we implement the 16 ports 10100 module. For example, now the 24-port 10100 module, which is not available yet, is going to be a similar design. However, in that case, we're actually going to have 3 shared memories that will actually look to the queue manager as 3 queues. And each shared memory is going to support 8 ports. But I think we should stick to what we have now. shared memory. Shared. Now, if we talk about physically how big those memories are, in the case of the gigabit module, we have 256 kilobytes per port. Okay? So this, in the case of the gigabit right here, this is 256K. Okay? It's a quarter meg. And that's per port. Now, in the case of the 10100 ports, we have a pool of memory here that is 1 megabyte of shared memory. This is a slide that is essentially identical to what I was drawing on the board in a slightly different configuration. But what it shows you is, it shows you what we call the control board. And as you remember before, I said the control board contains what, in this slide, it's called the CAM. CAM actually stands for something called the content addressable memory. But essentially, this whole block right here is considered the address resolution logic. And this block feeds the so-called arbiter. In this drawing, it looks like an arbiter, but it's an arbiter/queue management system. And that's a system that essentially you see here a signal that goes to a separate so-called control signals, control bus. And that's a bus that goes out and controls all the port modules and tells them what to send to what, when, on which bus to go. In addition to this, you also see the management here on the control module. You see the management interface here to one of the data buses. And here it's broken up in a little more detail. You can see the actual CPU and the various peripherals on the CPU. Our management CPU on the GFS actually has a private Ethernet connection besides, it has some serial ports, but it also has a private Ethernet connection so that you can, in some application, people like to build a separate management network. It's just a simple 10BASE-T Ethernet port that can be used just like an RS-232, only you can use it on a LAN. So that's the control side. And on the port side, again, this is broken in a somewhat more detailed version, although still simplified. So logically what we see, and this is a gigabit port actually, we have the fiber transceiver, that's just a physical layer to the gigabit. We have the so-called serializer, deserializer, that's a gigabit transceiver. Then we have the MAC. Then we have what we call receive input FIFO and transmit output FIFO. You can look at them as two logical separate memories. In fact, this is a single memory right here on the gigabit port. And we have what we call a header FIFO. It's called here an address FIFO. So that answers your question. Where does the header stripping happen? The header stripping in a gigabit happens locally for every port. This is literally a port. So what you see here is you see the MAC, you see the port controller, and that's essentially a device that moves the data from the MAC to the various memories, strips the header, sends the header out on the address bus to the address resolution logic, and also on the receive path, stores data in the transmit memory and reads it out to the MAC and sends it out. So if we did a quick so-called packet walk again, we see here is data comes in. This is a frame that actually got switched. Look what happened. This is a frame that entered on this port and got out on this port. So data comes in, the header gets stripped and sent through this separate memory on this separate so-called address bus to the address resolution logic. At the same time, the rest of the content of the frame gets stored in memory that's associated with the port. Now, the control information travels to the address resolution logic and gets a decision is made here what to do with this frame. That decision is forwarded to the queue manager / arbiter. That arbiter, when it sees that the port for whom this decision was made is ready to transmit, and the ports or port to which this frame is destined is ready to receive, he signals this port through this control path right here. He signals this port, see, through this control path. He signals him to go ahead and send this frame. He also signals the port that's supposed to receive it to go ahead and receive a frame. Now, what he also does is he signals on which bus this data is going to travel. And you can see here we have two data buses, bus B and bus A. And in this case, it shows you a packet that travels on bus B. So he signals these port controllers, and then this controller starts reading this data from the memory where it was stored after it was received, sending it on the bus and into a transmit queue or the transmit memory of this gigabit MAC. And then, of course, after that, all that remains to be done is to read this data when the MAC is able to transmit and send it out the wire. So that's the most basic level of data getting switched through And the important things to notice here again is how efficiently this is done, because we have three separate interfaces on the so-called backplane between the boards. We have a completely separate control signals, which are used to direct the traffic. We have a separate header bus, or we call it an address bus, that is totally separate from the data. And then we have two pure data buses, where nothing else travels on them but data. There's no header information, there's no control information, there's nothing but pure data that travels on these buses. So the system is incredibly efficient in handling this kind of traffic. So that's how a packet travels between ports. We also have another diagram here that shows how a packet moves around the switch if it has to go